Good morning, good afternoon, and good evening to everyone joining us today for this webinar. We would like to thank Jürgen Grötsch, our invited speaker, and the EAGE technical community on hydrogen and energy storage for organizing this event, and all of you for being here. And we hope you enjoyed the session and learned a lot. And with that, we will begin the webinar. So Belen, I hand it over to you.
Okay, thank you very much. Good morning and good afternoon, everyone. Welcome to our seminar from our EAGE technical community on hydrogen and energy storage. We are very happy to have here today Dr. Jürgen Grötsch. He will give us a very interesting presentation on this important topic of natural hydrogen. So I will first of all present our agenda. I will give you a short introduction in our EAGE technical community. Then we have the talk, and then we have a session of question and answer. You can write directly your questions in the chat and I will read it, or you can also raise your hand and then ask the questions directly. And then we have the closing. Next, please. Yeah, so a few very short introduction to our community. We are a network of members from different backgrounds of that include geoscience, engineer, business, economy, and we are interested in providing current insights, perspective, and the latest technical development within hydrogen and energy storage disciplines. So we cover different topics, as for example, natural hydrogen system, stimulated geological hydrogen production, policy, emerging energy value chain, energy storage that include electromechanical, chemical, technical, and mechanical storage. Our community has been created last year. It was established in 2024 and currently counts of more than 1,200 members. So here you can see our committee members. We are 12 members from all over the world, including Europe, UK, Australia, and the US. You can see that we are in academia, also in industry. Also, we have consultants, and all of us related with this hydrogen and energy storage topics. So our chair is Dr. Ellie Maxilians and Dr. Maximilian Haas. Here you can see our our activities as a community. We participate in the EAGE annual and the GIT conferences through dedicated session and participation in the events technical committees. Also, we are organizing different seminars or webinar series as the ones here today. This is our third one. And we also offer some news, career advice, and vacancies. So if you are interested in join our community and follow up our activities, you can join us in LinkedIn by scanning this QR code, or also look at us in LinkedIn, or approach us in the different EAGE conference. And just to remind you that next year we have the EAGE annual conference in Aberdeen and the UK in June. And if you are interested in participate, you can submit your abstract. The deadline is 15th of January. So be aware of that and please join us. So thank you for joining our webinar today. And now I wanted to introduce Dr. Jürgen Grötsch. Grötsch he is currently university lectured in geoenergy at Friedrich-Alexander-Universität in Erlangen, Germany. He holds a PhD in geology from FAO, completed in collaboration with the Scripps Institution of Oceanography and Vrije Universiteit Amsterdam. In 1991, he joined Shell International, where he held several senior positions in the Middle East and Europe, including chief geologist of NAM and head of the Geoscience Service in Europe. In 2011, he initiated the Open Subsurface Data Universe OS2 project, now the largest global digital technology initiative in the energy industry. Since retiring from Shell in 2022, his focus has shifted to sustainable surface solutions for the energy transition, such as natural hydrogen and geothermal exploration. As founder and CEO of Tellus Energy Solution, Germany's first natural hydrogen and helium exploration company. So thank you very much, Jürgen, for being here today and from present us this interesting talk. The floor is yours.
Thank you very much indeed for this kind introduction and opening the stage here for natural hydrogen and maybe some more. Let me first get the logistics right and start sharing my screen. Hopefully, yeah, works. Can you see my screen?
Yes. Yeah.
Yes, everything works. Okay. Yeah, good. Then we can head off. And yeah, thanks for having me here in this audience. And yeah, talking about natural hydrogen, it's something which we are doing now since something like 3 years, essentially, at the university, at the Friedrich-Alexander University in Erlangen, with a team of students. And in the meantime, we have made quite significant progress, I would call it, in that respect. And I will show you a little bit about natural hydrogen, why we need it actually, and also how we explore for it. But at the end of the day, the talk here is about how we can move from exploration towards production, and that is one of the crucial questions we have now and which we need to address. So let's first go into energy systems and look at actually what we actually what the challenge actually is. Trying to move my slides here. That does work very good. So you can see here actually some of the game-changing events which we saw in the energy systems man has used until now. And it all started with the Greek mythology when Prometheus gave fire to man. We were burning wood. We later on in Central Europe were burning a lot of peat. Interestingly enough, in 1880, it was not Shell or Exxon or BP or Total which dominated the energy market, but it actually was so-called peat barons, which still until 1880 in Berlin were actually the ones who distributed energy to people. So everybody more or less was burning peat. Peat was replaced by coal. Coal was replaced by oil in the 20s. And then since the 90s, we see a very strong shift also towards natural gas. But we also have seen what global change is like, and how our emissions, CO2 emissions, carbon emissions actually have grown over the last 100 years dramatically, and that's where the Paris Agreement came in 2015. A lot of companies would like to address that. A few nowadays are dropping out of that, like China and the US. Yeah, the movement is there towards a new energy system. And the question is, how does this new energy system going to look like? And clearly, there's two components which will play a major role, and that's solar and wind. But one of the challenges with solar and wind is the so-called capacity factor, and that's how we describe actually, the availability of an energy carrier in percentages, if you want to, and that is for solar we have a capacity factor of 0.25, and for wind it's something like 0.3, maybe if you're in a good offshore location, maximum 0.4. So you can see that is actually where the famous German word Dunkelflaute comes from. If both of these actually are not available, such a future energy system will not work. And that's why we need additional energy resources actually to join wind and solar. Now, one of them is, and that's what this group is focusing on, is actually hydrogen, and the hydrogen demand has been forecasted to actually increase dramatically over the next decades, and that of course would be desirable. Hydrogen is a fantastic energy carrier, and it burns very clean. But one of the big challenges is, of course, where do we get all the hydrogen from? And that's where we are standing at the moment. In addition to hydrogen, there is another major movement, and that will certainly become the third leg in this energy system of the future, and that is geothermal energy. Nowadays, we can produce geothermal energy anywhere on the planet almost, and that is due to the fact that we have many different ways, development concepts, if you want to actually produce geothermal energy. But one of many of them actually are totally underexploited or not exploited, and this shows you one here. Low temperature geothermal heat from aquifers in the range of between 40 and 50 degrees has a huge capacity, a gigantic capacity, which is big enough to make it a third leg in the energy transition, similar to wind and solar. And that is a little bit counterintuitive because everybody thinks about geothermal. It's hot, needs to be hot, very hot, but you can see actually in aquifers you don't have a lot of energy actually in the very hot parts of these sedimentary basins. Of course, volcanoes is a different story. There is great examples of development of volcanoes which actually can produce a large amount of power as well as heat or cooling. And that, of course, is also a future potential. It's not just heat, it's also the cooling potential. So these two are actually something which need to be developed further. And I show you hopefully at the end of the talk how this is going to work and how we are approaching that and how we are doing that. So keep these two in mind, hydrogen as well as low temperature geothermal heat. Now, if we look at hydrogen and go back and see, the hydrogen economy is facing quite a few significant challenges, and they can be described kind of in four dilemmas. One is the high cost of it, and that is both for green as well as blue hydrogen. The costs are significantly higher to what we are producing hydrogen at the moment with, and that is mainly fossil fuels for 99%, and costs there are significantly lower, between 1 to 3 euros per kilogram. For green and blue, it's between 5 and 12, and offshore is even more. So cost is one of the challenges. Competition for power is the next one. If we want to make green hydrogen, we need a lot of power, green power, and that is not available essentially. It also is actually a process which is not so efficient. If you can see my cursor here, the efficiency of making green hydrogen is actually rather low, so you lose a lot of energy on in that transformation from electricity to hydrogen. And then, of course, we have one of the biggest problems in our energy systems at this moment is transport, and that is, we don't know that only since hydrogen, since we have been looking into hydrogen transport. If we would liquefy hydrogen, we would lose 80% of its energy content. So not a very economic nor efficient process to transport hydrogen over long distances. So these dilemmas are there for hydrogen. They, of course, are also there for natural gas. If we look at the pipelines coming from Russia or the dependencies of LNG transport routes from various places like the Middle East or the US or from elsewhere. Now, the world has changed in 1987, and that is actually when people have discovered in a water well, which you can see on this left-hand photograph here, quite a large size well, 100-meter deep, a little bit more than 100 meter. And somebody threw a cigarette into that little borehole, a big borehole, I should say, and it exploded without a flame. And many years later, this story actually came to a businessman from Mali, and he actually set up the first production site for hydrogen, which you can see here on the right-hand side. This is the first and only production site for natural hydrogen in the world. And that was pure serendipity. And we know in the energy system, a lot is related to serendipity. Also, the Groningen gas field in the Netherlands is such a serendipity. They were looking actually for oil in the Zechstein, and by accident found the 10th largest gas field in the world under the city of Groningen. So you can see actually a lot of our developments actually are in the energy systems are actually related to serendipity, interestingly enough. Now, the question really is, how can we move from serendipity into structured workflows and development concepts? And but looking at that example, which actually produces something like 50 tons per year, and we don't know actually if it still produces, but it did produce from 2012 onward until recently. It's likely now that the IS is in this area, and we don't know if it's still operational. Nobody can access it or get there anymore. But it certainly has produced 12 or 13 years until now, happily, and produced electricity rather reliably for more than a decade. So if that works, if it works in one place, it usually also works in another. Then we would be able to address all of these four dilemmas I've shown you. And that is, low cost of production. This was very low cost of production, of course. You actually don't compete for power. It's quite highly efficient in this case of Mali, and it actually is independent of transport. It's a first example of a decentralized energy hub. And we will talk more about decentralized energy hubs for the future. But where are we standing actually? And I always like to make the comparison to the oil and gas industry. And the oil and gas industry, if you look at it, if you go back 150 years, that's actually where we are standing now with natural hydrogen. So we have an energy carrier, a hydrogen system, but we don't quite really understand it fully. Unlike now, after so many years, the oil and gas system we do understand quite well these days. So yeah, we are kind of back in time 150 years, and there will have to be a lot of developments to really change that. But let's look at what has happened so far in the industry and how can we actually classify the industry. And I try to do that in the next slide. And we have plenty of different colors of hydrogen. You mentioned blue hydrogen, green hydrogen. Here, let's only talk about white hydrogen and orange hydrogen. So yeah, these are two different types of hydrogen. And if we explore for these exploration concepts are rather similar, we use play-based exploration nowadays. We are mostly still using brownfield exploration, so we are exploring in areas where we already know there is hydrogen, like in Kansas, Nebraska, or in southern Australia. But we also are moving into greenfield areas, and that's what I'm going to show you soon in Germany. That is purely a greenfield area. We're using similar types of technologies, gravity, magnetics, geophysical tools. We are mapping source rocks. We're looking at gas and fluid samples, geochemistry analysis, and but then you can see actually that the industry is not quite that mature. And I've worked in the oil and gas industry 31 years, and there is a big difference between resources and reserves, and that is often actually mixed up in the world of natural hydrogen. We have now, Václav Skånik estimated recently in Paris at a conference that there is like 110 companies now exploring for natural hydrogen around the world in various places. But yeah, sometimes resources and reserves get mixed up. Now, if we look at development concepts, and that's really what we want to later on talk about, is actually we see 3 different types of development concepts for natural hydrogen. The first one, I call it aqueous hydrogen. That already tells you there is water and there is hydrogen in the water or associated with the water. The second one is a free gas hydrogen, and that is kind of comparable to a natural gas field, pressurized gas accumulations in traps like we know them from the oil and gas industry. We'll talk about that a little bit, if they are there or not. And then we have a third way of looking at natural hydrogen, that is the stimulation of natural hydrogen in ultrabasic rocks. And laboratory experiments have clearly shown if you use catalysts, you can actually generate decent amounts of hydrogen from ultrabasic rocks in the laboratory. And the idea is to also do that in the subsurface. But then actually, the question is, how can you produce that hydrogen back? We think we can stimulate it if we inject water and catalysts in the subsurface. But one of the big unknowns is actually how can you produce it? So all of these concepts have their challenges, and we don't need to go into all of them. You can look at yourself at leisure. Free gas accumulations we haven't found yet. There is no pressure data which actually documents that there is any free gas accumulation in the world so far, and that is a realization which is made more and more also in exploration wells which have been drilled. So it looks like that is something which is not so easy to find, and historically we have never found it in hundreds of thousands of wells in the oil and gas industry. we find actually hydrogen elsewhere outside of sedimentary basins where the oil and gas industry has not drilled. Stimulated hydrogen, the big question is how can you produce that? So also quite a risky business. And the only production site which remains we consider as an aqueous hydrogen site, so hydrogen dissolved actually in an aquifer. And that is what we are focusing on, and we have always focused on that right from the start with our startup Tellus Energy Solutions. Other companies focus on the other two streams, and some move from one to another, actually in between free gas to stimulated gas, but also maybe to aqueous hydrogen. So that is basically the industry in a nutshell, if you allow me. And this is really what we actually are focusing on in Tellus and also at the FAU in our work, in our project developments in southern Germany. So we want to move towards development, project development. Because one of the realizations we make is actually we know where to find hydrogen actually nowadays. And this is just one example. I was recently visiting, invited by the Bulgarian Academy of Science in Sofia. And they asked me if I can show them how to do gas sampling, soil gas sampling. And we went around in Bulgaria on a field trip. And then we came to a location in the botanical garden in the midst of Sofia and started measuring. And you can see here the results here, 270 ppm. The atmosphere has 0.5 ppm for comparison. So you see significantly elevated hydrogen concentrations already from this one-day experiment we did here in Bulgaria around the Sofia area. So essentially what we are saying is exploration is not the challenge anymore. We see now, and the more we look, the more we find, and everywhere around the world, we find new locations where unusually high hydrogen concentrations, natural hydrogen concentrations are reported. And the same holds true in southern Germany. The more we drill, the more we find, and that is also an old rule from the oil and gas industry. And that actually, if we summarize the literature, and if you look at play-based exploration concepts, then you can kind of classify 10 different types of geological settings where you can find hydrogen. And that is really the astounding thing. We see, unlike oil and gas, which we know is in sedimentary basins under certain circumstances, and we know it requires a source rock, seal, trap, and migration history, which is suitable to trap it. That is not the case in the natural hydrogen system, because we see natural hydrogen system. The system is working actually in many places outside of sedimentary basins. The most well-known probably is number one, that is Iceland here, and these are MORs, are mid-oceanic ridges. So from Iceland all the way down into the Atlantic, South Atlantic, we have plenty of measurements now that out of these mid-oceanic ridges and volcanic areas, we see actually elevated hydrogen concentrations coming out. Volcanic areas, other ones are volcanoes in the Philippines. I was recently working there in Asia, and that also shows very high concentrations in certain areas as well as in the ophiolites. Subduction zones, like in the Pyrenees, number 2 here, that's a cross section through the Pyrenees. And we see in many subduction zones, and surprisingly, actually, in rather in different ages of subduction zones, we see hydrogen, and that is the Pyrenees are probably one of the best studied places, but we also see it in the subduction zones of the Alps, and that actually, in the Ivrea zone in the Alps. That is also a more and more common place. We can find natural hydrogen. Ophiolites, almost everywhere where we have ophiolites, these are ocean bottom rocks, ultra-basic rocks, which are stacked on top of each other, like in Albania, in Oman, and Crete, and many other places around the world. Almost everywhere we have documentations, Turkey, that we have hydrogen associated with these ophiolites. And this is number 3, and that's probably the most well-known one. Also, that's where the eternal flames of the Olympic Games come from. These flames are burning already since man can think, and man has documented history, so more than 3,000 years, and that is flames which actually are south of Antalya, and they're still burning naturally. We have ore mines. This is a satellite image number 4 from a big ore mine, where you see actually these fairy circles, which are supposed to be emanations of natural hydrogen, and also in ore mines itself, in South Africa, in Canada, in Albania. In many places we have documentations that in shafts and galleries, natural hydrogen is actually encroaching into these galleries and shafts. Number 5 is the one I've shown you earlier from Mali. That's a cross-section here from this aquifer setting in Mali. In old cratons, be it in Africa, be it in Australia, or be it in South America, we see plenty of examples in Siberia, where actually in old cratons, hydrogen emanations have been documented. We see radiogenic rocks, and these are granites, huge granite plutons, and you see here number 6 with these fluid inclusions. In all of these granites in fluid inclusions, you see hydrogen, which are actually a result of radiogenic decay of uranium, thorium, and potassium. So radiogenic decay splits water into hydrogen and oxygen. And then we have another kind of a bunch of a play, which I call here the rift grabens. And this is the most well studied rift graben, which is surprisingly old, 1.1 giga years, so billion years. And that is a very old one in the US. And where the down where the red star is, that's where Nebraska, Kansas is. That's where most of the wells identifying hydrogen have been drilled to date. We have here Australia, the Cooper Basin, where we see actually in hydrocarbon systems, we see that hydrogen actually, we have oil and gas fields around in the shallower areas, but in the center, in the deepest parts of the sedimentary basins, I hope you can see my cursor here. You can see these colors, and that's actually where hydrogen is being generated. So also in sedimentary basins, we see hydrogen. And then we have salt mines, surprisingly in Poland and Germany, where we have documentations of hydrogen emanations. And we have aquifers, and that's what we think is actually one of the most common occurrences in aquifers, dissolved hydrogen. So surprisingly, many different geological settings where we have hydrogen. So that's why I told you, we are at the beginning of understanding this system. It's quite a complex one, much more complex than the petroleum system. Now, how do we explore for natural hydrogen? That's just like the tools we are using. We are using a hammer and a little iron rod here, 1 meter length, which is open, and we make a hole of 1 inch diameter and put a tubing in there, which blocks the atmospheric air to get into the borehole. and then we fix actually a pump and a hose, and we have a sensor here with a pump, and that extracts gas from 1 meter deep below surface, and that gas we are measuring. And in these measurements, we actually can see these dramatically increased concentrations of hydrogen, often higher than what these tools can measure, 1,000 ppm. We have another one which actually measures up to 2,000 ppm. We know there's more in there, but that's how much we can actually measure with these tools. And then we can go about and actually make maps. So geologists like to make maps, and that's how we do that. You know, we make all these locations. We have in the meantime made like 1,000 of these soil gas samples in huge areas. So we first start with a coarse network, and then we actually home in and zoom in and actually refine it and make contour maps actually of the concentrations of natural hydrogen in these soil gas samples. And that allows us to identify so-called hydrogen hotspots. That's what we are after. So we are identifying portfolios of hydrogen hotspots. And that is what we are doing actually in southern Germany. This is a geological map here of southern Germany, where you can see for reference Munich and Nuremberg. That's where the Erlangen is close by to Nuremberg, and that's where FAU sits. And we are working in northern Bavaria in these areas in several thousand square kilometers in the meantime, which we have looked at. And we have developed a play concept here, which makes us believe that there should be hydrogen, and there is hydrogen, I can tell you that. The resources are there, but the question is really, what are the reserves and what is actually can be produced from these resources, and only once we actually can prove that we can produce it, we can actually call that reserves. That's how we deal in the oil and gas industry with the question. Now, we have looked into these areas, particularly number 1 and 2, and that is basically where we have set up this portfolio of hotspots. And I show you actually why we're actually going in that area. And we also need a source rock, something which generates hydrogen. And the best and well-known studied process is serpentinization. Serpentinization needs ultrabasic rocks, so we need a stack of ultrabasic rocks. And so that's the first thing we need to identify. And we are in a lucky situation here in Nuremberg, for reference again. On the right-hand side of the geological map, you see actually Bohemia, Czechia, and parts of Germany, and that is a crystalline basement rock. And in that crystalline basement rock, we find ultrabasic rocks. And luckily enough, one of the deepest holes ever drilled in Europe, the KTB, the Continental Deep Drilling Program, has drilled down 9,101 meters, 25 or more years back, actually already. That was the deepest hole ever, and the most expensive hole ever drilled in Germany. That has retrieved a tremendous amount of data and core data, and in fact, a lot of ultrabasic rocks are there, 9 and more kilometers of ultrabasic rock. And what we know is also that this ultrabasic rock is not just in Bohemia, in the green box, but it's also underlying the sedimentary basins of the so-called Franconian Basin. So at the end, what we actually have is here, these ultrabasic rocks are derived from a set of subduction zones of Varischian age. So these are Devonian Carboniferous subduction zones, quite old, in fact, not as old as the ones, the rocks in Kansas, but old subduction zones, in fact, and they still produce plenty of hydrogen from these ultrabasic rocks being subducted. So that is the geological circumstances and setting for the source rock. We also look at migration, and you can see here there is a big fault between the Bohemian Massif on the right-hand side of the geological map and the blue area. This is the Franconian Basin, and you see a cross-section of one of these thrust faults. And these are actually the migration paths for hydrogen. And in fact, you can see that what's happening along these fault lines, hydrogen is migrating into aquifers and from aquifers also to the surface. And that's where we actually can map it. And the main reservoir we consider as the biggest aquifer suitable for this is the Buntsandstein, a very well-known oil and gas reservoir, also geothermal reservoir, fluvial clastic depositional system, and here you see a piece of core with the sandstone and the porosity, and then that brings us back to our geothermal low temperature developments, and this is exactly the rocks which have 50 degrees, 55 degrees maybe at 1500 meters, and they are perfectly suitable for low temperature geothermal developments. And we know they are aquifers which are over the whole area, like circled here in red. That's where the southern Germany Franconian Basin is located. And it's a formation something like 600 meters thick at a depth of something like down to 1500 meters. And that is really what brings here. We have some AI analysis where you see in yellow colors shown by the arrow here, the highest geothermal gradients in Germany. So they are similar to the gradients we see in the Rheingraben on the left-hand side here. So we have a very good heat flow here, and that makes it also in shallow areas ideal for geothermal developments. And that is when we started then our startup company, Tellus Energy Solutions, to make that into a field development project. So moving from exploration into production. Unlocking the potential for low temperature heat as well as hydrogen, and if we are lucky, also helium. And that's why we call it Triple H for the Americans who are used to AAA. The American Automobile Association. That is basically our concept here, looking at heat, hydrogen, and helium together. And that's what we call gas farming, gas mining, similarly to how other people have done that for CO2, for methane, for example, the Dutch glasshouse farmers. And that enables us to actually produce low production rates profitably for dissolved hydrogen gas. And because the costs are recovered via the geothermal development, and that dramatically reduces also the risk of development and therefore lowers the level cost of hydrogen dramatically actually, and makes it economically viable. Without the geothermal development, that would not look very good economically. So the combination makes it look, and then we play another trick here, and that is actually we're not just identifying hotspots for hydrogen and also geothermal reservoirs, but we are also mapping the opportunities we have for decentralized energy developments, energy hubs. So think about Mali, that's a small case example. We of course look at a little bit bigger communities, but we are exploring right around communities so that we can get around transport, that we can have decentralized energy hub developments and optimize systems in these areas for heat, cooling, as well as hydrogen, and make these integrated field developments. So that is basically what we are doing. And And that actually shows you that natural hydrogen is not really like oil and gas. That's why we don't want to compare it with oil and gas, certainly not with pressurized gas reservoirs, because we don't think they are there. But we rather talk about net zero gas mining from aquifers. And this has been done for CO2 in Italy, in Ladrello, in a famous old geothermal development area. But it also has been done by Dutch glasshouse farmers, which have geothermal developments. They're mining, they don't mine hydrogen, but they mine actually methane together with the geothermal heat. So this concept actually doesn't just make it economic, but it also provides, of course, increased security. These decentralized energy hubs are certainly, a lot more secure for the future than major blocks of nuclear reactors like in Zaporizhia. You can see what that actually results in. So how do we develop that, and what do we do with the hydrogen? And we have a full-fledged economic model together with a scenario-based approach. We have actually plenty of opportunities to work with the hydrogen, and that the simplest one is catalytic combustion. We have a highly efficient process to generate heat from hydrogen, which is dissolved in water. And that is available. It's not the most economic way of extracting hydrogen, but that certainly is one way to deal with. The second one is there is plenty of gas network providers which would like to get hydrogen into their gas network to reduce their carbon footprint. And that's blending, the blending option. And then once we get a bit more clean hydrogen, we actually, which is also a little bit more expensive to develop, we can do power generation via fuel cells, or we can go into the most economic option, which is actually mobility stations, so gas stations with hydrogen. And that is about the quantity we actually think we can produce from such aquifers in the future. So not steel plants or ammonia plants, but think about smaller developments, but economic developments. And this is really where we want to develop value with a development project like Kairos from the Greek mythology. We are identifying portfolios of hotspots. We are working together with the local stakeholders, so who are interested in heat as well as hydrogen. So we actually turn around exploration and production. So we look at where are the communities and the off-takers, and then we explore. That's different than most exploration companies work. They explore and try to see if they can get some volumes, and then they think about how they can get some value out of that. We don't think this is a good idea to work like that in natural hydrogen, but we want to turn it basically around and have production drive exploration. And then we also work on new solutions to actually produce that. So we have handed in the first patent on the engineering solution for that already with the European Patent Office. And that actually then is around how we efficiently can separate different gases from water, but also how to economically use that gas. And then we also look at offtake, and that is part and parcel of the development concepts. We need to get off-takers for the heat as well as the hydrogen, but that's not a problem really. The more difficult is to get enough offtake for the geothermal heat. And that is what this proof of concept Kairos is about, so that we can use that and replicate that in Germany, but also in the rest of the world. And that's really, if we come back to our original slide I showed you about the natural hydrogen industry, these 110 mainly exploration companies, they usually show you a high risk, high reward plot in exploration. So we show you a different type of plot, actually how you actually can look at it, and that is actually how to look at the risk and the financial exposure you have. So if you plot these three different types of development concepts of stimulated hydrogen, highly risky, also gives you quite a bit of financial exposure. If you do the free gas exploration, very risky. We haven't found any so far, no pressurized hydrogen reservoirs so far. We know there's quite a few aqueous hydrogen locations, and that's actually what we are focusing on with Tellus and what we want to develop so that we have a second development after Mali, preferentially in southern Germany. And that is what we are doing with our colleagues from the Friedrich Alexander University. You see here the names and students, but also with the startup. That QR code leads you to the Deutsche Welle TV movie, which was recently launched. Deutsche Welle is kind of like BBC World for Germany. It's an English video which explains a little bit more about how we are working and what we are doing. And that is Tellus Energy Solutions, the company with the people. And you can also scan that QR code to get to our website. So thank you very much for your attention. And that's where I want to stop at this point in time. And any questions are welcome. Over to you, Belen.
Yeah, thank you very much, Jürgen. Very, very interesting talk. We have some questions here, so you can write in the chat. The first question was from Chu Yan Xiang. Hello, thank you for the EAGE opening in thinking on hydrogen. I wonder what are the HSE considerations while managing a hydrogen EIP, exploitation and production project?
The HSE considerations are very similar to how you operate geothermal projects and how you operate also then gas facilities on the surface. So there is nothing unusual around natural hydrogen in that respect. We, of course, have to look at seismicity, induced seismicity, and we're already preparing for that nowadays. We can set up micro seismicity monitoring stations for baseline surveys, as well as any induced seismicity. For the gas handling, that is kind of standard types of approaches. Nothing unusual.
Okay, thank you. So another question, Paromita asked, can you use the gas pipelines for the transportation of hydrogen in Germany?
Yeah, that is something which we don't really want to do. As I mentioned, we don't believe in major hydrogen gas pipeline networks across Europe and the world. We don't see that happening, but we want to actually utilize the hydrogen locally, and we have plenty of ways of getting rid of the hydrogen. That is not a problem. Actually, people would like to get too much hydrogen, more than probably we can produce. So local usage and as little transport as possible. If we would have to transport it, we would also consider things like in the quantities we talk about, like liquid organic carriers, for example, which have been recently developed for hydrogen.
Okay, so Paromita raised the hand. Maybe you want to ask directly?
Yes. Just as a follow-up to the question, in general, do you have consumers right in the vicinity of your production area that you can directly use the hydrogen? Because you mentioned
Yeah.
you want to use it locally. So is there any kind of fertilizer plants or, I don't know, mining industry? And the same applies for the geothermal heat that you'll generate, because I assume you need consumers very close to avoid any kind of pipelines or
Yes. Yes.
transportation heat.
Yes, we have both for heat and for gas. We have off-takers, local off-takers, and as I mentioned, we have on purpose explored in areas which are close to consumers. We can't transport heat for long distances. We need local consumers, and that's why we actually are exploring around the consumers. The consumers want the heat, and we provide them the heat. And we have other consumers, other industries which want the hydrogen, and that's what we provide them with. Yeah, we have both.
Okay, thank you.
Okay, so the second question, is already answered. Another question from Nazmul Hakemondal. Could you share the full timeline for developing your project in southern Germany?
Yeah, we think we can do that in the most complicated case within 5 years. If we take a simple case, one duplet only, we can shorten that timeline.
Okay, great. Arnaud Evert, interesting presentation. 3 questions. What would you do with non-sellable gases you may encounter? Aquifers typically contain CO2, nitrogen.
Yeah, that's a very good question. We actually have an off-taker who is interested in everything. Maybe nitrogen we can't produce economically, but even CO2. That has off-takers. If we can produce clean CO2, for example, the beverage industry needs a clean CO2, bottled CO2. So there is also people who use CO2 in industries, and also for that we have solutions. Yeah, as I said, nitrogen also, of course, has consumers. But there we would not be able to compete with nitrogen extracted from the air. And the second, Arnold, if I read that off here, if you want to export for blending into a power plant, how do you dehydrate the gas? Dehydration is not a problem. We have actually, as part of our patented solutions, we have actually, there's a dehydration unit in there, so that is not considered a big challenge. That's a standard piece of engineering which we can attach to the facilities. And then number 3 is, how do you mitigate the risk of production impairment and scaling, which typically increases with brines rich in dissolved gas? Yeah, that is a common challenge in geothermal developments. Having said that, actually, the deeper you drill, the hotter the fluid is, the more problems you get with scaling. As I mentioned, we are drilling in lower temperatures, lower salinities, and less deep, 1500 meters, and therefore we expect actually less scaling than in high temperature basin developments. But yes, we have to consider that and bring that into consideration. But it's a smaller problem than in other geothermal developments.
Okay, thank you. Then another question from Taufik Nathan. When do you think the first drilling for natural hydrogen will be start in Europe or in Germany?
We are planning, we hope we can do that in 2027. Maybe not in the first quarter, but we hope we can do it in 2027.
Okay, so in 2 years, yes. The next question is in German, so you can read it.
Sind Daten und Harzverurteilung für alle Geothermie, thermalwasser Bohrungen in Deutschland verfügbar? Yeah, that's a question on data availability in Germany, subsurface data availability in Germany on H2 content and drilling results. That is a challenge in Germany. I have mentioned this repeatedly to the German government because we have a federal system of 16 states and one federal geological survey, and they all have their own database system. So we can get access to data, but it's a little bit more difficult than compared to other countries like the Netherlands or Norway or Canada or Australia. So it's a little bit more complicated in Germany, but we historically we have collected all the data, but it generally takes a bit longer in Germany.
Okay, thank you. Yeah,
So
Paulita, you
is it okay? Is there time for one more question?
Yeah, sure.
Okay, so I thank you so much for the presentation, and I just wanted to come back to the slide where you mentioned about resources and reserves. So this is something which I struggle to understand, that in case of hydrogen, even the resources are actually quite a difficult estimation. It's not like the geothermal heat in place or the oil in place. So already getting a volumetric estimate of resource is something which is still I don't know, under, I think, evaluation. And then on top of that, we have to make estimation of reserves. Do you have any suggestions, any feedback for somebody who would like to go towards this direction? Yeah, thanks.
Yeah, a very, very good question, and you're absolutely correct. We don't have any standards for natural hydrogen until now. And that actually, requires also a more understanding of the hydrogen system. Because if you use aqueous hydrogen as your model, that is very different from doing volumetrics on pressurized gas reservoirs or volumetrics on stimulated hydrogen, orange hydrogen. So I think this question is not answered at this point in time. But of course, what we can do is, if for aqueous systems, we know what the solubility of hydrogen is, and we also think we know what is probably the replenishment of hydrogen along migration paths. We know from mining studies in Canada, from Barbara Sherwood's Lola and the Trochet group from Albania, we have quantitative estimations on how much hydrogen actually per year comes to the surface or into the mine. So if we take these numbers, we can get some estimations on what is replenished as well as what is dissolved and what we actually can produce from that.
Okay.
But not the classic volumetrics you are used in oil and gas or in geothermal even.
Yeah, thank you.
Yeah, so someone raised their hand, and I think Arno, you wanted to ask something?
Yeah, Arnold, yes, indeed. Thanks, Arnold, for that comment. That actually they have made an attempt to quantify that in their paper. You can see that in the chat. That's correct. Thanks, Arnold, for adding this. That is probably the first time that we have a good estimation on volumes involved in aqueous hydrogen systems. Arnold, you wanted to say something, or? Yeah.
It's not perfect, but I start. Okay.
No, that's great. We need someone to start somewhere.
Yes.
Yeah. I also have a question, but maybe, yeah, this is not solved now. But do you think that the exploitation of hydrogen, so the production, can have any negative effect? For example, if hydrogen leakage to the atmosphere is not as bad as oil and gas, for example, that we have CO2 emissions. But do you think that hydrogen production can also have this kind of bad side, or?
Yeah, in principle, hydrogen can be an indirect a greenhouse gas, but you have to imagine that so far in none of the climate models any natural hydrogen has been considered to date. And the estimations around are that there's like 23 or maybe 100 million tons per year actually naturally coming to surface. So we have a process here which happens actually not just on planet Earth, but in many planets. We see actually that hydrogen is naturally coming to surface and into the atmosphere. So essentially, basically what we are doing is trying to grab it before it reaches the atmosphere or somebody else reaches it, and use it for energy and transform it from hydrogen into water, essentially adding the oxygen. So essentially what we're trying to do is to prevent hydrogen coming into the atmosphere and catch it in the aquifer.
Okay, thank you. Any other question or see in the chat? No. So, okay, if there is no question, we thank you a lot. Jürgen was very, very interesting, and yeah, it's nice to see how the hydrogen future is rising and going to a nice continuation. So, and thank you all for attending, and thank you for your questions.
Yeah, thank you very much for your inviting me, and have a good evening or a good day, maybe I should say, the Australian way that covers everything.
Yeah, thanks a lot. Bye. Thanks
Good day.
to all.